Okay, so we're going to pick up where we left off last lecture. And at the end of last lecture, we ended up with two maybe surprising facts. The first is that for calcium, the atom, the -1 anion is the most stable state. So not the neutral species, but the -1. Also, we learned or admitted that in compounds like calcium oxide or calcium sulfide, then the calcium 2+ cation exists. So we have these two facts that we need to reconcile. First, that it's true, what you probably learned in high school, that calcium 2+ is what we expect to find when we have compounds like calcium oxide or calcium chloride or anything like that. We predict calcium to be in the 2+ state because it would lose 2 electrons to get to the noble gas configuration. That's what you've been told. But last time we saw that if I just had calcium out on its own, I would expect to have it in this anionic state here. And actually, just to sort of like lead us off, the situation's even a little bit worse than this. So if we also consider, since we're talking about like calcium oxide, calcium sulfide, if we also consider sulfur, then what we find is if I go from like sulfur neutral and I want to add in an electron to make sulfur neutral into sulfur -1, and then I added another electron to go from sulfur -1 to sulfur 2-, probably again from sort of what you learned in high school, you would predict that this sulfur 2- would be the most stable state. But if we look at the energy changes associated with this, so we go and we calculate like we did for calcium, the delta E associated with this first step, then we would find that this is -0.43 RH. And so this first step is exothermic. It is true that we give off energy when an electron is captured by a neutral sulfur. This is just like what we saw with calcium, right? When I look up here again at calcium at the top, what we find is that I have the negative species because calcium can capture an electron, and that's exothermic. If I go ahead and calculate the next step here to get the sulfur 2-, which is again what we would naively expect from high school level reasoning, this we would calculate to be plus 0.15 RH. And so this step is endothermic, or energetically uphill. So the take home from this is that it is the sulfur -1 here that is the most stable state. Again, this is for in vacuum, meaning there's just only a sulfur around. And so now we have another set of facts, which is not only is calcium anion the most stable state, we also have sulfur -anion is the most stable for sulfur. But it's also true that in calcium oxide, or let's think about copper sulfide, since we picked sulfur, then S2- exists. All right, so now we have a series of observations that we need to somehow reconcile. And what we should be doing when we see things like this, where we notice that essentially in isolation, I expect the calcium anion to be the most stable, and the sulfur anion to be the most stable, but that in compounds we find these as calcium 2 plus and sulfur 2 minus, there must be some additional energetic driving force for this. There must be some reason that we can come up with. And kind of the clue to think about what's happening is that I have calcium 2 plus and sulfur 2 minus. And so when I see the 2 plus and the 2 minus, what I should be thinking about is Coulomb, right? There should be some sort of Coulombic potential that exists between these two ions. And I know that I have a positive charge and a minus charge. And so that I know that the overall interaction will be attractive, or that we go to lower energy when these interact. So we can start to try to diagram that. So let's imagine that we had our calcium 2 plus. I'll put it here. So this would be calcium 2 plus. And then we also had our sulfur 2 minus, but these are going to be in isolation. So we've been treating these as if they weren't interacting. And so I'll draw them very far apart here. The reason that this is important is that I can then consider in Coulomb's law not only the charge, but I have to know the distance between the charges. And so here, if we remember that the Coulomb's law is equal to E is K Q1 Q2 over R12, the distance between them. Here we might say R12 is effectively infinite. They're not interacting. And then if I think about the Coulomb energy, if R12 is infinite, that must mean that the energy of the interaction, so the energy between 1 and 2, is 0. All right. Another way, of course, we could have written this instead of 1, 2, we could have said the energy associated with the interaction between the calcium and the sulfide is also going to be 0. But in a ionic compound, this is not what we expect. We expect that these two species will be in close contact with one another. So I would have a calcium 2 plus, and then I would also have associated right next to it the sulfide 2 minus. So then I have to rethink what the distance is between these two. If I wanted to find the distance between the two, maybe the easiest way to do it would be to find the radius associated with each one of these, right? And so what I would end up with is maybe the radius for the calcium 2 plus, and then the radius for the sulfide 2 minus, and then the distance that actually separates these two, what we had been calling the R12, is going to be equal to the radius of the calcium cation plus the radius of the sulfide anion in the 2 minus state. Now, there's a couple different ways that we could go about figuring out what these distances are. One is that we could calculate this. And when we were thinking about calculating things like the energy of atoms and things like that, we came up with another simple formula where we could calculate the radius. And so you could go back and do that. The other thing that you could do, of course, is you could just look these up. And if we do that, what we find is that the radii, so the R for calcium 2 plus is going to be 1.03 times the Bohr radius. And then the radius associated with the sulfide 2 minus is going to be 1.04 times the Bohr radius. So they're pretty similar. And that must mean that in this particular case, the distance between these two, R12, is going to be equal to 2.07 A naught. Now, I am ready to plug these numbers into our Coulomb's law calculation. And so I know that the energy associated with this pair here is going to be K Q1 Q2 over R12. There's lots of different values that I can find for K if you look them up. I think the most convenient one for us is going to be 1,386 angstroms times kilojoules per mole. So that's what the value of K is for us, 1,386 angstroms. So again, angstroms is 10 to the minus 10th meters, kilojoules per mole. And so what you can see from these units is that I don't need the elementary unit of charge. Charge is not present in these units. So when I think about Q1 and Q2, I can just use the charges that seem natural. So +2 and -2. When I think about R, I can see that the distances are in terms of angstroms. And so I need to convert the value that we have for our R in terms of A naught into angstroms. And the conversion that I have for this is that A naught, and I think we saw this before, is 0.529 angstroms. So that lets me convert the radii that I have here. So I just multiply that by 2.07, and that's what goes in the bottom here. So this ends up being 1.095 angstroms. And then you'll see that when I run this calculation, I'm going to cancel angstroms. I'm going to cancel the charges don't need to be canceled. And I end up with units of energy in terms of kilojoules per mole. And so now what we find is that if I calculate the energy associated with 1,2, or what we would have said before, the calcium sulfide in this particular case, is going to be minus 1,952 kilojoules per mole. So this is what we find in terms of the interaction, the Coulombic interaction between these two. So this is the Coulomb energy for a pair of ions. So Ca2 plus and S2 minus ions. So if we go back and we think about what was happening here, we were saying that the calcium minus and the sulfur minus were the most stable. That means that if we were going to have calcium 2 plus and sulfur 2 minus, there must be some additional energy that helps overcome the energy cost I'm going to pay by making calcium 2 plus and sulfide 2 minus. And here's the start of this, right? That we have this Coulombic energy. In other words, what I could say is that the energy now associated with this ion pair is going to be equal to the change in energy that is required to generate calcium 2 plus the change in energy that's going to be required to generate sulfur 2 minus, plus this delta E Coulomb, the interaction between these that we just calculated. If you go back and look at the numbers that we had from our last lecture, we could convert what we had calculated in terms of RH into kilojoules per mole. You were given this conversion previously, and so I'm not going to walk us through this conversion. But basically, the calcium 2 plus is overall going to be quite endothermic, right? It took energy to take away the first electron. It took energy to take away the second electron. So overall, this ends up being plus 1,332 kilojoules per mole. That's to generate the calcium 2 plus. Then I need to generate the sulfur 2 minus. And so the first step is exothermic by 0.43 RH. The next one's endothermic by 0.15 RH. The overall process going from sulfur to sulfur 2 minus is going to be exothermic. So I expect a negative number, but it's not going to be as exothermic as if I had stopped here at sulfur 1 minus. But I do expect a negative number. This would be minus 366 kilojoules per mole. And then we just calculated what the E Coulomb is associated with this. And so we can go ahead and add in that next, which was minus 1,952 kilojoules per mole. And so that must mean that this overall energy is minus 986 kilojoules per mole. All right. And so this overall ion pair generating the ion pair is exothermic. The driving force, the reason why we can make calcium 2 plus and sulfur 2 minus is that when we make that ion pair, we get back enough Coulombic energy in order to offset the price we paid to get to the 2 plus and the 2 minus. If you go back, and you can do this if you want, if you go back and you calculate what's the energy associated with going to calcium plus 1 and sulfur 1 minus, and then what's the Coulombic interaction between them, and add them up, you'll find that it's not as exothermic as this is. If you went and you calculated what is the energy associated with calcium 3 plus and sulfur 3 minus, and then you calculate out what the ion pair interaction is, it won't be as exothermic as calcium 2 plus and sulfur 2 minus. So the point here is that we can't just consider these ions in isolation. We have to think about the interaction between them. And actually, we can go a little bit farther than this if we want. It's not just the fact that we have these as ion pairs, because when you have something like calcium oxide, it's like a big rock. It's something you can hold in your hand. So there's more than just 2 of these. So what we can do then is we can think about what happens if I have more than 2, right? What the simplest case might be is that I have a calcium 2 plus, and then I have a sulfide 2 minus. Whoops. Sulfide 2 minus. And then let's just think about what happens if I add in one more calcium 2 plus. So now I have 3 things. It's kind of interesting because when I think about what's happening here, I can see that I have this ion pair right here that we've already thought about. And if I think about just the energy that's associated with the Coulombic potential, we already calculated this. It's minus 1,952 kilojoules per mole. But then if I look over here, I have another one of these. And so I have another 1,952 kilojoules per mole. Now, everything's not perfect because in addition to thinking about these 2 attractive forces, I have to think about the fact that I have a calcium and another calcium, and these 2 things will interact with each other. Now, we could sit down and try to calculate this out, but there's a much easier way to do this, which is in this case to realize here I had a +2 and a -2 interaction, and here I have a +2 and a +2. So the numerator is essentially the same, but just of different sign. And then these are twice the distance apart that these were here because I have 2 units separating them. So essentially, I'm going to change this to be a positive number. It's repulsive, and it's going to be half the value. So 976 kilojoules per mole. All right. What that means is that the E Coulomb associated with the trimer. Okay, so we have a little bit of notation here. Tri means 3, mer means things. So I have 3 of these units. So it's a trimer, is going to be minus 2,928 kilojoules per mole, right? And so this is more stable, lower in energy than the dimer, right? The dimer was our pair. So we can see that despite the fact that I have this repulsive term here, the overall energy benefit is favorable. And I expect that if I had 3 things like 2 calciums and a sulfide, I would expect them arranged like this rather than one pair and another calcium out on its own somewhere. So this pattern will repeat itself actually over and over and over again. And what you'll end up with is something where I have built up a lattice. So let's go ahead and try to draw that out. So a lattice would look something like this. So here would be all the calciums, the 2 pluses, drawn in blue as we have above. And then I would have all the sulfides sitting here, interpenetrated with them. And so we're building up what we call a lattice. Then this lattice would extend in 3 dimensions so that if I wanted to try to think about how this looked, there would be like something behind this red one, and then a red one behind this blue one, and so on into the background, right? We're building up essentially a shape that looks like a cube. And then this cube is packed with these chemical species. So now we have essentially an infinite number of pairs that we have to account for. And how do we do that? Well, we can start trying to do that. We could say, all right, let's take the perspective of one of these calciums. So let's just focus on this one here for fun. All right. If I think about what this calcium sees, then it's going to have a neighbor here, a neighbor here, a neighbor here, a neighbor here. And then again, I said this is in 3 dimensions. So there'll be like a neighbor behind it and a neighbor out in front. Okay, and so let me try to draw. There would be like a neighbor back here and then one up in front somewhere here. The point of this is that each calcium 2 plus has 6 sulfide 2 minus neighbors. Okay. These neighbors are all at a distance that we just calculated. Let's call it R, just for easy reference. Okay. We know the energy of interaction between these pairs. This is the energy that we've been working with, right? At R. And so the energy for each pair is going to be minus 1952. All right. It's a little hard to see this, but we'll try. Usually we have like a nice model that we can use for this, but okay. This same calcium has another calcium sitting here, another calcium sitting here, another calcium sitting here, another calcium sitting here. And then there's like another 4 of these behind it, rotated 45 degrees, and in front of it, rotated 45 degrees. And so it ends up that we have 12 calcium 2 plus, and these are a little bit farther away. So let's call this the next nearest neighbor. Okay. And if we think about the distance that this is away, it's essentially, if I went up R and over R, I would end up at this point that we just thought about. And so that must mean that the distance I can calculate as the hypotenuse. And so this will be at square root of 2 R. Okay. That's going to reduce the energy. That's fine. Okay. But there's 12 of them. And then if we keep going and I look for like the fact that, let's see if there's even like a color worth trying to do this with, purple, I guess. Okay. There would be another set of red or the anions that we could associate with that would be not just like over R and that way R, but also like back into the page R. And so what that will mean, and I know this is maybe hard to see, so I apologize, is that there will be 8 S2 minus next nearest neighbors. Okay. And these will be at basically 3 right turns in 3 dimensions. So this will be at root 3 of R. Okay. And that will have also an energy associated with it. So what we would do is I would take this 6 and multiply it by this energy pair. I take these 12 and multiply it by the energy here, the energy here. And then I would just keep doing that for infinity. All right. So we sum over an infinite number of such things. One of the things you're probably learning if you're taking calculus right now is just because you sum an infinite number of things doesn't mean you get infinity. Some of them converge. All right. And so this will converge in this case. The series actually has a name. This is the Madelung series, if you care to read about it. And we will get a value at the end of the day being 3,000 or negative 3,093 kilojoules per mole. And so something that's kind of interesting about this is here was the value for the trimer, which was 50% larger than the value of one of these like dimers that we saw here. By the time we add up all the infinite number of these that we have, we're just a little bit bigger, right? This would be the energy for the entire lattice, the entire solid. It's still more negative, and so we will form this lattice. But something that's kind of interesting is that most of the energy that we get from having multiple neighbors is already present when we just have this trimer. And that's something of interest. Okay. So we're kind of nearing the end of this, and there's 2 things I want to say about this. One is that when we make a trimer, we're already start to see the big benefit we have. And it emphasizes the importance of understanding that these ions aren't just in isolation, okay? That they interact with each other, and that the Coulombic interaction is a driving force for making these ions. Not only that, as we get more and more and more species, we get more and more and more stabilization. And so that's what drives this lattice formation. But, and I guess what we're explaining here is ionic bonding. And so this is kind of the end of ionic bonding for this course. We're just trying to convince you that ionic bonds are largely driven by these Coulombic interactions. And when we say that, we don't just mean it's the Coulombic interactions that hold it together, which is, again, probably like the high school level understanding that you were given, but it's even what drives the formation of the ions in the first place. Something else, though, that you might consider is that if I had this trimer that I've drawn, I drew it like this. And the reason I drew it like this is that if I have like the positive charges here and the negative charges here, these 2 repel. And so maybe it makes sense that I would expect these things that have the same charges to be on opposite sides as far apart as they possibly can. However, when we look at something like, let's say, water, probably again from high school, you realize that water is bent. But we also said that I have a dipole moment of water along these bonds that looks something like this. In other words, what I have is a partial positive charge on these hydrogens and then a partial negative, maybe 2 amounts worth on that oxygen. It looks a lot like what we had here. But here we said that the repelling charges should move these as far apart as possible. They should be on opposite sides of the negative charge. But in water, we know that's not the case, that there's an angle here that's not 180 degrees. And so there must be a reason why. There's, again, some sort of energetic reason for why we're not obtaining this angle that's exactly 180 degrees apart. And it turns out that this is due to building up covalent bonds that require the presence of orbitals. And the orbitals may not be distributed appropriately for these 180 degree angles. That idea of how covalent bonding works is what we will be doing next time we get together after Thanksgiving. And so I apologize that we just had a drawing where you had to look at a bunch of like 2D stuff like this. But I guess that's what happens when it snows. Hopefully y'all have a wonderful Thanksgiving.